Welcome to our lecture today, and we'll be talking about how we convert base 10 to base 2. And the reason why we're going to be looking at this, one is that I think at some point in the 150, 250 experience you should look at binary numbers, and two, because this is what the current, one of the labs is based off of. So the lab that deals with recursion is the lab that we're going to convert a base 10 number to base 2. So we're going to walk through how to convert, look at binary numbers, and then to look at the lab real quick. So let's do that. So base 10. Base 10 means there's 10 possible digits, and that is our normal numeric, 0 through 9, 1 through 10 number system that we deal with. Okay. When we look at binary, then we just simply move to only having two numbers, so zeros and ones. Why do we care? Well, because computers at the lowest level it's all binary. So at some point in time, understanding binary will probably serve you well. With that, how do we read binary? Okay, well, the numbers are read from right to left, and they're all positions that are a factor of 2. So if we look at any of these four values here, that's 1, that's 5, that's 10, and then that is, of course, 3510. So they're read from right to left. If you've never done this, a chart like this can help you. So each position in a binary number, we start here, and then we read in this direction, and each position represents 2 to the power of, so we start with 2 to the power of 0, 2 to the power of 1, and so forth until we have no more binary number left. And so if we go back a slide, and let's say that we look at the binary number 1010, well, I'm claiming this being base 2 is equal to 10 in base 10. So if we write that number 0, 1, 0, 1, and then these are all zeros, then all we have to do is look at, this is 2 to the 0, I'm sorry, ignore that one. We just look at where we have a 1. Okay, so we have a 1 in this position, that's 2 to the 1, and we have a 1 in this position, that's 2 to the 3. That is 8, and that is 2. So those are our base 10 equivalents. We add those up and we get the value 10. Same thing here, just a little bit different number. If we have the binary number 1001, 1001, okay, we read that from right to left. Any position that has a 1, we figure out what it's 2 to the power of. We figure out the base 10 equivalent, well, 2 to the power of whatever is a base 10, but we do that factorial, or not factorial, but that exponentiation. We get the value, and then we put it down into here, and we add it up. We get 153 in this case. Of course, your calculators can do this really well. If you've never entered into scientific mode or programmer mode or whatever operating system you're in, it can convert. You can type in a base 10 number and say, oh, now go to binary, and it'll do it. Or you can do the opposite. You can type in a binary and say, hey, go to base 10. The reason we have to understand this is because that is the purpose of the lab. The lab will be to enter in characters. Remember when we looked at strings, we know that each character has an ASCII value. That ASCII value is in base 10, so it's an integer value. We can take that integer value and we can convert it into binary. So how do we convert? How do we convert base 10 to base 2? And we can use modulus. That's the way I want us to use to solve this recursively. There are other ways to do it, but I want to use modulus. So we can simply take and we can, if you think back to the last lecture, and we're looking for a structure for a function, for a recursive function that can take a number and solve it. Well, with this we can use modulus, and you're going to have to think a little bit differently here, because in the factorial example, the whole purpose of that function was to return a value. With this, in this particular program, the whole purpose is simply to print a value. That is our return. We're just going to print. The structure that we want then is we want to take the number. So let's say that I want to convert 64, and I'm going to use modulus to convert it from base 10 to base 2. We're going to start with that value, 64, and we're going to mod by 2. That prints our value out, and then we're going to divide by 2, and then call itself recursively. So the recursive steps will have a value of 64, then 32, then 16, 8, 4, 2, and 1. Okay, we know that this then is our base case, very similar to the example of the factorial. The difference is here is that we're printing off the value of modding that number by 2. Okay, so 64 mod 2, we print 0, because that's what any number mod 2 is 0, and then we call itself recursively divided by 2. So 64 divided by 2 is 32. So this is essentially our recursive step. Now we take 32 mod 2, we print the result. I'm sorry, not anything mod 2 is 0. Any even number mod 2 is 0. Sorry for the misspeak. So 32 mod 2 is 0. Okay, so we have 32 though, still, we haven't reached our base case, it's not 1, so we divide by 2, and we have another recursive step. Okay, now we have 16 mod 2, we print 0, and, well, we first check, have we reached the base case? No, so we print 0, and now divide by 2 and call recursively. Okay, and we just keep doing that, all of these numbers, because 64 is an even number, and every time we divide by 2, it's going to result in an even number. We just keep calling recursively until we reach 1. Right, 2 divided by 2 is 1. 1 is our base case, so we print 1, and now we're done. Now our function can return, and in this case, we are going to return all the way back to the top, but we're not returning a value with it. When we looked at factorials, we returned a value and then we multiplied by that return value. In this case, we've already printed off these values, so we don't have to worry about that. We just need to return. We need to stop the recursive steps. So you can see here this number, that's 64. If we go back to our table, let's go back to this one. What did I say the number was? 0, 0, 0, 0, 0, 0, 1. So 6 zeros and then a 1. So 1, 2, 3, 4, 5, 6, and 1. And if we look up here, that's 64. So yeah, obviously our value is 64, so that's correct. So we solved that. We converted 64 into a binary number. We plug that binary number in our table, and we saw that it is 64. So we know that it works. All right, a couple things I want to look at then before we actually look at the lab itself. Hopefully this makes sense. What I'm trying to get at here is, let's go back and look at that factorial function, but let's think of this as a recursive function that doesn't necessarily return a value. Okay, so there's some key differences here in how I structured this. We still have these two branches of logic. That is, we have an if branch and the else branch. The if branch doesn't do anything but prints a value. Okay, so once we've entered this branch, we've reached the base case. Inside the else branch, okay, kind of the same thing here. We can print something off. Okay, in this case, we're printing off 1s and 0s. And then we can call ourselves recursively. Okay, I didn't change the name, so please don't confuse this that I'm still using the factorial function. I'm just trying to give you an idea of how you can modify this in order to solve this lab. So we print our 1 or our 0, and now we call ourselves recursively again. Okay, and we'll do that until we reach the base case. So as long as we enter into this else branch, we're going to print and call recursive. Every single time, there will always be a recursive call. When we finally reach the base case and we enter this else branch or the if branch, then what do? Well, our program execution goes from here. We enter we exit the if branch, and now we go to this return keyword. Okay, and that stops the recursion. We've reached the base case, and now we can return. You could do it like this as well. You could say return right there. We've reached the base case and now we return. The thing I just want to point out is that you don't always have to, just because a recursive function doesn't always have to return a value. It just has to do something, call itself recursively, break it down. You know, in this case, if we go back and look at the slide, the complex case is 64. We don't know what to do with that yet until we reach 1. And that is because with each case, we need to print off what is the value mod 2. So 64 mod 2, we print it. Now we break it down to something that's maybe not solvable yet, but it's less complex. 32 is less complex, so 32 mod 2, we print it, 0. And we do that until we've reached our determined base case, which is 1. we don't need to break this thing down anymore. We know what to do because once we get the value, once we've divided that number by 2 enough times to reach 1, we're done worrying about it. We've solved our problem. All right, I'm going to go ahead and pull up the lab itself here. Let's see if I can find it though. Don't worry, we won't go through all those lectures. So lab 5, and this is what you'll see. Mainly here, yeah, you don't need to worry about this big screen capture. But I'm giving you a lot of the code. Okay, all you need to do is implement the logic inside of the functions. How does this look? Okay, so read through here, and what all this is trying to say is this here. Let's take a look at the actual program. So I'll run that again, and you'll see that I'm going to enter in some characters. Okay, and what I'm looking for is just your alphabetic characters, upper and or lowercase. So if I enter in A and I hit enter, then my program will convert the character A. We know that it's a char, so it has a numeric value, converts that into binary, and then tells me how many ones are inside that binary number. Okay, if I type in ABC, ABC, so lowercase and uppercase, we know those based off the ASCII table have 2 different numeric values, then it'll print lowercase and then uppercase. This is what it's converted to, and these are the number of ones in each one. Okay, so that's what the lab needs to do. If you look at the lab itself, this is what I've provided you with. Okay, you don't need to modify anything in main. All you need to do is implement print and binary printer. The hints are that this is how you're going to read the keyboard, the input. Okay, here's our scanf, here's our %C. You know, don't worry about this. EOF just means end of file. It just means that we've hit the enter key and we've stopped receiving input on standard in. This is the only call to print. Okay, that's the thing I want to point out the most here. Our only call to print is here. It's inside this if. So print is called just that one time. Binary printer is only called once from print, and then inside binary printer it calls itself. You have to decide and develop that recursive structure. Okay, so use the factorial code as a starting point. I don't want to give away too much, but you can definitely pause this video here and use this as kind of an idea to help, hopefully to help. And of course, this lab isn't meant to stump anyone. I'm not trying to create anything that's unreasonably hard, but I do want to provide you with a challenge. So, you know, with this isn't something unique. This isn't like I just created this cool lab to convert base 10 to base 2. Well, I guess cool is arguable. You know, you can find this solution on the internet. Be careful though, because a lot of the solutions they may not be recursive, or they may not work exactly the way I'm looking for it. But you know, if you need to use that as a resource, you know, I mean, feel free. I certainly can't stop you. But if you get stumped, you know, don't spend an exorbitant amount of time on one particular issue. I'd be more than happy to look at the code that you've already written and point you in the right direction. So that's it. Hopefully this is all making sense. Let me know if you have questions, and I'll talk to you next week.